Okay, so this is the last presentation for this morning. It's going to be given by Thomas Rushton on microcontroller-based network client towards distributed spatial audio.
Thanks very much, Roman, and thank you all for having me. Great honor to be here in such a esteemed company. So, my name is Thomas Rushton. I've been working with the Emerald team based here. I'm a second year master's student, I'm on an internship here, but I'm a student at Aalborg University in Copenhagen at the moment. So, what have I been working on? Network distributed spatial audio, essentially. So, there's been recent interest, I guess, past couple of decades, especially in immersive audio experiences, VR, AR, sound spatialization, that sort of thing. Certain techniques, ambisonics and WFS is one that I've focused on. These call for large numbers of speakers. Consequently, specialist hardware, powerful systems, centralized, and probably in situ, not mobile or flexible, really, to speak of. So what if we could create an alternative, something that is flexible, that's scalable, it's adaptable to other purposes, it's maybe it makes use of distributed computation, maybe it's low cost even. There we go. Okay, so focusing on WFS as I did, I think it's useful to give a little background just to start off. So what is WFS? So it's essentially it's a form of, to give it its grandiose description, acoustic holography. That's how Burkhout put it in his paper from 1988. So the dotted lines here in the diagram indicate sort of per speaker delay lines, or rather the control data that's used to describe those delay lines, or from which those are derived. Ultimately, like in working out what the delay lines should be, we can throw away, this is an XY coordinate system, we can throw away the Y coordinate for the length of the delay lines and just keep it for doing things like simulating the changing gain with simulated distance from the speaker array, and also for the say low-pass filtering, since high frequencies will be lost more readily to the air, the medium of transmission. What this indicates, though, is that in order to create these simulated wave fronts here, the blue lines, there needs to be a good deal of synchronicity between the speakers in the speaker array. And this sort of system is going to need a lot of audio I/O. Each virtual sound source is going to be a distinct channel of audio, and the WFS algorithm is somehow going to have to be connected to a lot of distinct speakers. So that comes back to what I was saying before about a centralized system. So, oh, sorry, I forgot to advance my slides. So what if we could turn that into something like this, where we've broken down this monolithic algorithm into something that's distributed. So each of these distributed instances still needs to know where each of the sources is. It also needs to know which speakers it's in charge of, but it only needs to produce output for in this case, 2 of those speakers at a time. So this brings us on to the topic of networked audio. What is networked audio? What's it being used for? So we had a great talk on JackTrip earlier on from Nando, and so that has, particularly during the pandemic, supported things like remote rehearsals. It also supports large-scale professional live audio systems. And what platforms, protocols exist to support networked audio? Well, there's JackTrip, as we heard. There's the The Jack audio connection system contains the NetJack protocol. There's Jamulus, which is another popular jamming platform during the pandemic. There's Dante, which I think is a proprietary system. That's a sort of one that comes up in professional large-scale applications. So why not just send audio? Why send as audio over sort of traditional audio cables? Why send it as network information? Well, the distributed case I was hinting at a moment ago, say each of those individual modules only has a limited number of I/O channels, but we want to support a large-scale system like WFS. We may be able to send more channels over a network than we could simply using regular audio channels. So what are the limitations? Okay, well there's the size of the datagrams that we can send over our network protocol. In terms of the UDP protocol, which is something that JackTrip, for example, is a layer on top of, the maximum datagram size is 64 kilobytes. But in practice, this is limited further by the maximum frame size, the MTU of the underlying protocol. In this case, it's going to be Ethernet, and that's going to be around 1,500 bytes, but that's going to be hardware specific. In addition, there's things like default socket sizes on your hardware. There's also how server software has been structured. Can we send data over UDP multicast, for example? And is there some kind of threading model in the server software, for instance? Okay, so taking this idea on and thinking, okay, so how can we use networked audio to create a distributed WFS system? Let's look at the hardware that we employed. So we used a TNC 4.1, or rather several TNC 4.1s. And so this is the small collection of objects from which our modules are constructed. There's a TNC 4.1 here. It's got an audio shield and built-in Ethernet functionality. For a microcontroller, I would say it's pretty powerful. So it's got a pretty solid CPU, a good amount of RAM. It supports audio buffer sizes, well, modifiable audio buffer sizes. I found it could run down to about 16 samples reliably. There's no OS, there are no threads. It's a double-edged sword. That being the case, everything runs on hardware interrupts, essentially. And so this has ramifications for timing. It's pretty good in terms of its timing, but in terms of implementing sophisticated processes, it can be somewhat limited. As the name suggests, it's pretty small TNC. It's about 6 centimeters in length. And it's affordable. It comes in at about 30 euros. So let's now look at the kind of how the system was developed, the audio server for a start. So to the left we have Jack, the recursive acronym Jack Audio Connection Kit, and this is an inter-application routing system for audio and MIDI. And then there's the JackTrip protocol, which uses as its backend Jack as its audio server. So this is the command for starting JackTrip as in hub server mode. So the capital S is hub server. Q is the packet buffer length that JackTrip will use. And P is an auto-patching mode, so whether any clients that connect to it should be connected to each other, connected to themselves. The number 5 says no auto-patching. Patching can subsequently be done using Jack's API for connecting ports. Any client that connects to a hub server, as long as it sort of does so in the correct way, will appear in Jack, in the routing graph, as an audio device with a number of I/O ports specified by N here, the final argument to the hub server. Okay, so one of the attractions of using JackTrip for this was its comparative simplicity as a protocol. To get a client to communicate with JackTrip and start exchanging audio as encoded as UDP data, so 8-bit words, is to start by sending a handshake over TCP. So the client says, hey there, JackTrip, here's my UDP port. JackTrip goes, cool, I'll start a send and a receive thread for you. And, well, it doesn't tell it that, but that's what it does in the background. What it does tell the client is, here's a UDP port that you can reach me on. And that's kind of it, really. From there on, the server and client just have to maintain this flow of UDP packets, send and receive, essentially. And that can continue ad infinitum. So, I mean, the client could be another JackTrip process running on the same machine. It could be a remote machine that knows the appropriate IP. It could, in our case, be a microcontroller that, again, knows the correct IP and initiates this handshake and then starts exchanging, audio in UDP packets. As long as the client keeps sending those packets with the correct structure, the correct headers, it'll stay connected. And yeah, the only condition is on this packet structure here. So what I found was timestamp and sequence number actually kind of don't matter. I mean, they could be helpful in terms of diagnosing things like synchronicity, but the things that do matter are the sampling rates have to match. And Nando may correct me on this, but buffer sizes have to match as well. Otherwise, I mean, particularly for the client, as we implemented it, the buffer sizes have to match. Otherwise, you get malformed packets. It's difficult to decode those into audio data. Okay. So from there, we can deal with multiple clients. Each of these makes that TCP handshake, initiates a flow of UDP audio data. But here it's informative to make a distinction, I think, between what's happening in terms of network communication on the one hand and audio routing on the other. And so that looks like this. Clients are connected to the server and they're exchanging UDP packets as described. And what we can have is an audio application that's not necessarily a JackTrip client. It's just something that exists within the Jack audio routing system. It's sending, that can, via that system, send audio to the JackTrip clients. And this can be, as I'm illustrating here, multiple channels of audio. So here's kind of an architectural overview of our system. So now, and I thought my diagrams were going to get quite convoluted and difficult to follow. And then I saw Nando's, which were very impressive. But yeah, so now the initial system is fading as the background. We have this main overview. Our audio application is sending audio over UDP into the Teensy audio library. It's being received by this JackTrip client, sent to a WFS algorithm, which is going to Teensy's outputs. And the client can also send audio back to itself that then gets sent back into Jack over UDP. In turn, the WFS algorithm, which was implemented in Faust, consists of taking the incoming audio sources and creating this kind of, let's see, for the speakers that the Faust algorithm knows that it's in charge of, it creates this, how can I put it, this view of the virtual sound field, basically, and then sends it to its two output audio channels of the Teensy. And then additionally, we've got this WFS controller, so that is sending audio essentially to Jack, that JackTrip is then handling over UDP. It's also sending control data in the form of OSC messages. And these are actually being multicast to all the clients that are connected at that point in time. So there's a particular address range that's, let's see, reserved for UDP multicast. And so the Teensies are all subscribed to the appropriate multicast address, and the application is sending control data. So it's telling each client where it is and which speakers it's in charge of. It's also telling each client where the sources are, and then the Faust algorithm does the rest. So what are the challenges here? Okay. The big one is clock drift, temporal inconsistency. So what I found is that TNC's timing is pretty good, really good in fact. So the interval it's reporting between audio buffer increments is really steady. I think at a 16 sample buffer, it's something like 363 microseconds, and that's, yeah, it's the average time reported by TNC stays very close to that average. The server and network, less reliable in this regard. So yeah, the rate of UDP transmission does not equal the audio clock for anything. So this requires compensating for the fact that during a given hardware interrupt on TNC, when it's hoping to receive a UDP packet that it can use for audio purposes, there's probably going to be one available, but there might not be. And then the next time there may be two, and so on and so on. Here's a little sort of debugging view that I used. So this line here shows, and this was for a 32 sample buffer, the minimum and maximum don't stray too far from the mean for the receive side, so it's TNC, for send for the TNC, and then receiving from the server, there's a much bigger variance here. So how can we compensate for this? Essentially, the approaches that I employed was to treat the server and UDP input as authoritative, even though, as I've just described, the server is pretty unreliable timing-wise, but it's the source of the audio, so it has to be treated as authoritative in this case. And then, so receiving the audio samples, writing them to a circular buffer, and then by a process of adaptive resampling, compensating for the fact that, there's drift in terms of the read and write positions to that circular buffer. So, as best as possible, keeping the read position about one buffer behind the write position. This involved employing a fractional read buffer index, adjusting that position relative to the delta between the read and write positions, interpolating and smoothing, and ultimately, and I say this not meaning to be too facetious, but keeping fingers crossed and kind of hoping for the best. So that being said, how does this perform? So with a block size as low as 16 samples, things were running pretty stably. I tried down to 8, and that was about the limit. 16 works stably enough, 8, and things didn't seem to kind of hold together. The FPGA people in the room are going to hate me for saying this, but latency, 1 to 10 milliseconds. This is dependent on what block sizes are being used. This is in terms of measuring output from the server as UDP, and then being sent out by the client as audio, and then sent to another machine to record it. So there's latency at a bunch of steps here, including the input on whatever audio interface is being used to make the recording. So the true latency from the server over UDP to the TNC and then as audio output is certainly less than 10 milliseconds. It's pretty low. More importantly though, the synchronization it's quite good. The clients are synchronized to within about one buffer. And so that's with the proviso that there are occasional glitches. The system as implemented could be certainly refined in terms of refining that, synchronicity between the server and clients. So just to illustrate, so this is sending a low frequency square wave that you can see at the top from the server to some clients, and then back into an analog input on a sound card. So obviously the ADC there has you know, smashed this square wave to bits. But you can see that the latency there is around, actually you can't see the numbers here, but the latency from the server to the clients and back to the audio interface, it's about 7 milliseconds here. But what we see is that between the two clients pictured here, the offset is, it's a handful of samples. We're in the sort of 20 sample sort of range here. And this is running with 8 clients, and so the spread here is, it's within this was running at a buffer size of 32, and the spread is, it's high 20s somewhere. You can see the individual sample points. And the offsets do vary over time because each client is adjusting itself relative to what it's receiving from the server. But so although the offsets drift, they do so within this range of, let's say, 20 to 30 samples for a block size of 32. So let's see, there's more that could be done here. For one thing, the system is designed to assumes a local network, but this platform, the JackTrip client on a microcontroller, could be used for things like, as described earlier, for remote rehearsals, or creative installations, these sorts of things. There are other spatialization techniques, ambisonics, for example. Better synchronization could be possible via multicast. Multicast is not supported by the JackTrip protocol. NetJack does support multicast, but it's a more sophisticated protocol in some ways to interact with. It's something that we began to pursue, but ultimately it's sort of escaped the scope of this project. But yeah, certainly something for future work. Alternatively, there's using an external clock, but that starts to make the system less accessible, less useful for maybe packaging up and having as a self-contained device. Plus something like precision time protocol would require specialist hardware again, so that defeats the initial purpose of making things sort of accessible, flexible, and so on. There's alternatively options like maybe trying to tweak TNC's clock on the fly, adjusting its PLL, but having experimented with that, I imagine it's possible, but for the kind of application that we were trying here, I found it to be pretty, unstable, difficult to manage. And also, it would be interesting to try and implement something in a truly distributed fashion, so something without the centralized server, or perhaps a server running on a more sophisticated single board or microcontroller, something that maybe runs an OS or has threads. But yeah, it would be nice to try implementing as much as is required to run a server on the TNC environment. So you could have one microcontroller as a server and a bunch that would then connect as clients, for example. Okay. Anyway, thank you very much, and I welcome your questions. I also will be demonstrating the system as it stands upstairs this afternoon. So yeah, thank you very much.
Questions? Maybe you guys are hungry? I can't really ask questions because I was Tommy's advisor for this project, so I feel, but
I mean, you could if you wanted.
I think I know the answer, so. Oh, yeah, Nando?
Yeah, have you, very interesting.
Thanks.
Have you considered other protocols other than JackTrip?
Yeah, as I hope I just alluded to.
Some.
Yeah, NetJack was one that we looked into. I mean, Stefan, you were instrumental in the development of NetJack, and I think We think it should be possible.
It's,
But the way that NetJack is structured, I started trying to unpick it, but it's just going to take me or someone else more time to do so, to create a kind of reduced client implementation. Like as I said, JackTrip has this massive advantage of being so lightweight in terms of making that initial connection and getting things going. Yeah, NetJack, sorry, it assumes the availability of a threading model, essentially, a native threading model.
you may consider also creating your own non-protocol, which would be just sending raw data.
Yeah, I mean
recovering the clock from the data arrival.
Yeah, I mean, you'll forgive me, but that sounds like that's how protocols are born, isn't it? I think. I mean, yeah.
We don't have enough, right?
No, indeed. But yeah, I mean, that idea crossed my mind. That would be a way to go, kind of. Particularly if everything was contained to the microcontrollers, then yeah, a dedicated TNC Jack protocol of some kind would be.
I did something similar.
Yeah.
A long time ago, so we should talk.
Yeah, we should.
Yeah.
That would be great. Thanks, Nando.
Other questions?